So in this additional sample problem for the LRC circuit powered by an AC source, we'll look at the case where all these three elements are connected in parallel instead of in series. Now, even though the method, the idea is the same, that is, when we draw phasor diagrams, okay, the results are very different because when they're connected in series, they have the same current running through each one of them, but their voltages add up. So I have to draw a phasor diagram for the voltage additions, VR plus VC plus VL equal to the total voltage epsilon. This time, they all share the same EMF. Each element is exposed to the same EMF epsilon, but the currents add up. Right? This current I running into point A is split three ways into IL, IR, and IC. So what I need to do then is to draw a phasor diagram for the currents. The current phasor for IL, the current phasor for IR, and that for IC. You add these three phasors together, you will get the current phasor. I is the total current. So let's see how we can draw that. Okay, so you can see here we equated all the three voltages, but added all the currents. Let's look at how to find IR, IL, and IC in relationship to the EMF. Okay, for the resistor, that's the simplest. For the resistor, I have epsilon maximum equals to IR times R. The epsilon maximum is actually I shouldn't write epsilon maximum. I just write epsilon. That's the most. That should be the most general expression. Epsilon maximum is only the magnitude. So let me rewrite this. I have epsilon equals to IR times R. Okay. So therefore, if I were to draw a phasor diagram for epsilon and a phasor for IR, you know they have the same phase angle because R is just a number. Okay, so let me draw a phasor for epsilon as a reference. So here's a phasor for epsilon. Then I can then draw the phasor for IR because they have the same exact orientation like this. This is IR. And what is the magnitude of this phasor IR? IR magnitude simply equals epsilon maximum divided by R. Okay, now let's look at IL and IC. And we saw the relationship between the voltage and current in each element when we studied them in parallel, in series. The same relation holds true this time here as well, because you know, if you consider only V and I for one element, okay, it doesn't matter how this element is connected with the rest of the circuit. It's all the same. For example, I still have VL equals L times DIL dt. And if IL is a sine function, then VL will be a cosine function, meaning that VL always leads IL by 90 degrees, the same result that we saw before. And therefore, I can find the current going through the inductor to be 90 degrees behind its voltage, therefore 90 degrees behind epsilon. Okay, so I can draw the phasor diagram for the inductor, the current in the inductor, and it goes this way, 90 degrees behind the phasor for IR. Okay, and what is the magnitude of IL? The magnitude of IL is simply the amplitude of the voltage going applied to the inductor, which in this case is epsilon maximum, divided by its reactance, which is omega L. It's the same as we saw in the lecture, in the previous lecture. Okay, similarly, I can find VC, how it's related to IC. So VC equals to Q over C, and that is 1 over C times IC dt. Okay, now if IC was a sine function, then when you integrate over the sine function, you're going to get a negative cosine function. Now, cosine leads sine by 90 degrees, but a negative cosine function falls back by 180 degrees. So overall, VC trails IC by 90 degrees. Okay, as we saw before. So VC, of course, is the same as epsilon. And therefore, IC should be, I should draw IC 90 degrees ahead of that. And so let me draw that. Again, I'll use a different color. So this will be IC, okay? It leads IR by 90 degrees because it leads epsilon by 90 degrees. So my job now, actually, before I do that, let me write down the magnitude. Let me write the magnitude of IR. I'm sorry, IC. IC it should be equal to the amplitude of voltage applied, the amplitude of the voltage applied to the across the inductor, the capacitor, which is epsilon maximum, divided by its reactance, which is 1 over omega c. So this is equal to omega c times epsilon max. This is the same as before, okay? So my job now that I drew the phasor diagram for each of the currents, this is to add all 3 phasors of IC, IR, and IL. Now, you can see clearly the easiest thing for me to do is resolve the sum of IC and IL first, because they're just opposite to each other. Assuming that IC is greater in magnitude than IL, as the way I drew it, then the sum of these 2 points along the direction of IC. And then I have to just simply add to that the last phasor left, which is IR. So it's like this. Okay, so the total phasor, again, I'm going to use a different color. Okay, a different color. That's the total phasor. And that is the phasor for the total current, I. And there's an angle phi between epsilon and I. Now I can find both the magnitude and the phase angle phi. The magnitude of the overall current. The magnitude of the overall current, let's see what that equals to. You can see from this right angle triangle here, I maximum, according to Pythagorean theorem, the square root of IR squared plus what? IC minus IL and then squared, right? Okay, so let's work that out. So what is IR? The magnitude of IR, and that, as you know, is epsilon maximum over R, and you square that, right? And then what's the magnitude of IC? That equals to epsilon maximum omega c, and then minus the magnitude of IL, which is epsilon maximum over omega L. You square that. Okay, you can factor out the epsilon maximum, and then you can find the expression for I maximum. So I maximum equals epsilon maximum times a factor, and that factor equals to 1 over R squared plus omega c minus 1 over omega L squared. This is very different from what we saw before. What we saw before, there's not 1 over R, it's just R. Okay, not 1 over R. And then what we saw before, omega L was in the numerator, but this time omega c is in the numerator, so it's different. Okay, so that's the magnitude. What about the phase angle between the overall current and the EMF? That is, what is the phase angle phi equal to? Well, you know, you can see here, tangent phi equals what? Equals opposite over adjacent. So that equals IC minus IL divided by IR. Okay, you can do the algebra here. You can plug in the numbers. IC goes like 1 over omega c. Actually, no, it's the other way around. It's in a numerator. So IC goes like omega times c and then epsilon maximum, but that's going to cancel out. Minus 1 over omega L and then divided by R. Okay, so that's the result. I have found the resultant current. The resultant current is that I equals to, as a function of time, equals to I maximum, and then sine of omega t plus phi. And that, because why is plus phi? Because you can see here, obviously, the current phasor leads the epsilon theta by a phase angle of phi. Okay, and so that's our result. And so what is the value? What is the expression of I maximum? What is the expression of phi here? Right here. Okay, and we can also find the overall impedance of the circuit. Impedance Z is defined as, you know, the amplitude of the driving EMF divided by the amplitude of the total current, I maximum. Okay, and what is that equal to? Well, that turns out to be equal to this. 1 over R squared plus omega C minus 1 over omega L squared. This is, again, very different from the impedance of the LRC in series. Back there, you didn't have the 1 over thing business, and R was just R instead of 1 over R here. So you can see here we have the same idea, but very different results because we're adding the current phasors instead of adding the voltage phasors. So be careful about that. Okay, don't just copy the results. You have to understand how they're calculated and find the correct result.